What I'm describing as an experiment, I am qualifying as being a formal experiment. So this is not like you doing an experiment with a piece of hardware, or you doing an experiment trying to find out the impact of a certain say type of diet on your body weight outcome. What we are talking about here is a formal experiment, which means a designed process that happens before the experiment to identify the components of the experiment, controlling things as we go along that we don't like them to affect the result of the experiment, collecting data and doing statistical analysis on the collected data. So this is what is referred to as a formal experiment. Now, why do we do experiments? Why are experiments important? How come they are used in all these fields I've mentioned? Experiments involve collecting numbers, and numbers are better than subjective opinion. Okay? So if we go back to the topic of user interface, what about this? I give you two user interfaces and I tell you go and interview users, interview 40 users, and show them the interface you're building, and ask them, do they like the interface or not? And if they like the interface, you come back and tell me, oh, okay, my users like the interface. Okay, if 30 out of the 40 like the interface, then perhaps the interface is good. Okay. Now the problem with user opinion is that in many cases the user is not able, or you're not able, to measure the user feedback objectively. For example, how would a user perceive an interface being good? Is it because the color theme matches what he likes, or is it because he thinks this is a good interface while it's not really a good interface? Okay, so what's even worse, if you're trying to measure efficiency, if you actually ask someone how efficient is this, and you describe to him a process, or you describe to him a mechanism, it's very difficult for users actually to perceive speed of execution. So when they talk about something being fast, it's relatively fast to what they know. Okay? When they talk about something being slow, it is slow compared to something they have done before and they think it should be done better or faster. But the word slow is not quantifiable or qualifiable on a scale. Neither is the word fast. You know, that slow means 5 or 7 or 10 or 12. Okay? So in many cases, actually, the users will not be able to quantify the performance they are asked to quantify. Now let me give you a motivating experiment so you get the idea of, you know, why do we do experiments. Okay, let's say your keyboard at home got damaged for some reason. Okay, and you go to a shop and you ask him about buying a keyboard. So he shows you 3 keyboards. One is for £60, typical Chinese keyboard, and no-name keyboard, and a Microsoft keyboard for £500, and some strange-looking keyboard for £750. So for sure you should be getting interesting at that point. Is like, why would I pay like almost 12 times the price of a standard keyboard? I mean, 750 compared to 60 is just a ridiculous multiple. So why? So you grab the box for this X keyboard, and you start reading on the back of the box, and it says that if you use this keyboard, you decrease your chance of getting your nerve in the multiple carpal syndrome, which is basically a damage that happens to the nerve in the hand because of repetitive use of a keyboard. And they might also tell you, oh, okay, and by the way, if you use our X keyboard, you will type 20% faster. So if your average typing rate on a regular keyboard is 40 words per minute, well, in our keyboard is going to be 48 words per minute. Now you stand and think, okay, how can I verify that these claims are actually accurate? Because anyone can claim anything. Now the question is this true? And this will only be true and provable if they have done an experiment. without an experiment is just a claim. So if they cite for you, this is scientific research backs up our keyboard, that our keyboard, if you use it, it's 20% faster, and you're 25% less prone to carpal tunnel syndrome, then yeah, okay, go ahead and buy the keyboard. But if they don't, it's just a claim. It's not based on scientific inquiry. It's just their claim. It's a marketing claim, basically. Okay. And you could think of many parallel examples in our day-to-day life. Companies putting advertisements for products that they claim will do amazing things to the consumer without actually backing it up by a formal proof. And the formal proof here is actually an experiment. Okay? And usually if a company makes an experiment, they will say so. They will say this has been backed up by research, and they might even tell you like the researcher name or the location where the experiment was conducted in. Okay? Now you understand something very important. No one should make a claim unless it's backed up by an experiment. This doesn't include just keyboards, as I mentioned, all kinds of products. Okay? And in countries where companies are actually made liable for the adverts they put, the companies would be very reluctant to claim anything about the product. So if for example, it's a shampoo company, a company making shampoos, and they put an ad that says, you will decrease your chance of getting depressed if you use our shampoo, they will immediately get sued by consumer groups, because that's a claim that, unless it's backed by a formal experiment, it's basically a lie. Okay? So, well, in Egypt, sometimes you actually see adverts that are put, and they claim certain things, and that are not entirely, that are not true. Actually, they have not been verified, but because of the lack of consumer groups in Egypt that can go ahead and sue companies. We have the process in Egypt, but it's not well tightened. So we have commercial courts, and people can sue companies, and companies can sue companies, and NGOs can sue companies, but it's not as well established as abroad. And sometimes, when I'm watching TV, I see all kind of claims for things that are not proven. It's just claims. So the issue is, experiments are important, and they are done in various fields to prove what we call a hypothesis, which we're going to discuss soon. So I hope now you start to appreciate how important it is, even for a company, to claim something, that they will need to do an experiment. So what do we measure in an experiment? An experiment is a systematic process that is usually done in a lab or under certain conditions outside the lab, and we measure things. And the good thing about experiments is that it's not based on the user's subjective opinion, it's based on empirical measurements, it's based on numbers. We will collect numbers and do statistical analysis on these numbers, and then make claims based on our findings. So what do we measure? We measure 4 broad things. We call them research questions, and every research question will make you measure certain things. Okay? Now, the first research question: does X cause Y? Now, an example here is, does smoking cause cancer? Does eating a grapefruit every day causes you to lose weight? Does drinking 2 cups of coffee before an exam causes you to get a higher mark? Okay? Now, what I'm talking about here is called the research question. And this is the first step you do in an experiment. You define the research question. And once you've defined it, you cannot change it later on, because everything will be dependent on the research question that you start with. So you cannot start with a research question, collect the data, or basically design the experiment and collect the data, analyze the data, and then you find out, oh, okay, the data is not what I want, so I'm going to change the research question. But if you change the research question, you have to redo the experiment now, with the different things or issues considered. So once you pick a research question and decide on to follow this research question, you cannot change it. Now, if you actually look at the second research question, do X and Y covary? Okay, is there a relation between X and Y? Here X and Y represent anything, so it could be like, two keyboards I'm comparing. Now, here I'm asking for what we call a correlation in the second research question. Okay. In the third research question, I'm asking, is X better than Y, which is usually abbreviated as, is X greater than Y? In the fourth research question, I would ask, how often does Y occur? So for example, you might go to a village in Egypt and you notice that whenever you talk to someone, he tells you, oh, he has diabetes. So if you're a medical researcher, you would wonder, okay, does this village, is there something about them that is different from the rest of Egypt? I mean, Egypt, we have diabetes, but not everyone has diabetes. So there is what's called the national percentage of people who have diabetes in Egypt. Let's say they are 8%. Now the question is this village also follows the national average of 8%, or is it more? So there are statistical tests and experiments conducted to find out how often does a specific feature or disease or practice occur compared to some known established number that has been found also by scientific inquiry or through an experiment. Now, if you look at these four questions, you will notice that they're not different from each other a lot. In fact, if I say, does X causes Y? Does smoking cause cancer? Can't I reformulate it to, do smoking and cancer chance covary? And the answer is yes, you can reformulate any research question to be another one. But the problem is, since everything afterwards depends on your research question, you cannot change it. The differences are very subtle. Okay? If I say, does smoking cause cancer? Or does using X keyboard make me type faster? So does X keyboard causes faster typing? It is different from saying, does the more I type on the X keyboard, the more I type faster? Okay? Obviously, if I give you any research question, you can more or less twist it to be another research question. But since everything afterwards depends on the research question you start with, you shouldn't be doing that. Okay? You shouldn't be jumping in the same experiment between different research questions. You would pick one and then you would continue on without changing it. And what that implies is you got to be very careful when you pick the research question. Okay? In most cases in HCI, it's going to be, is X greater than Y? Which means, is this better than that? Because what we do in HCI is we come up with alternatives, designs for doing something. Let's say I would like to find a way to speed up the clicking on an icon in an interface, following Fitzlow's ideas that we've discussed earlier. So I will come up with one interaction technique, one way of doing this, and another way of doing this as well. And now I would like to find out which way is faster. So this is X greater than Y. And that's what we do in most of the cases. You get someone developing a new keyboard, and he would like to prove that if you use it, the typing speed is going to be faster, or the typing speed is going to be improved. So again, this is X greater than Y. Okay? Or you can get someone who's designing a new type of mouse, and he would like to compare it to the traditional mouse, and he would like to prove that the new mouse is actually will enable you to acquire targets faster. So again, this is X greater than Y. Okay? So X greater than Y is very, very common in HCI, but we still see do X causes Y and do X and Y covary. Now, the last question, how often does Y occur, is less common in HCI. It's more into the realm of medical studies and pharmaceutical studies. Okay? So I don't really talk a lot about it here. But It does exist as a research question, and you could design an experiment around it. Okay? For business purposes, for example, you could be interested to ask the question like the following: Do Egyptians living in Maadi buy more cosmetic products compared to the general average? So if you'd like to answer this question, this is about the fourth research question: how often does Y occur? Okay? Or do people in the summer buy more swimming gear compared to the winter? So again, you can formulate this how often does Y occur? So here's the takeaway. We do experiments to come up with a global finding. A global finding means it is applicable to all humans on Earth. This is pretty radical. We do an experiment on a handful of participants and we generalize to the whole 7.6 billion humans. What's the story here? The reason why all scientific disciplines and all, including also business and economics, are very interested in experiments and they do experiments is because of the power of experiments. Experiments are not about drawing a conclusion for the participants whom you're conducting the experiments on. Experiments are about drawing a conclusion that is applicable to all humans on Earth. And this is very, very radical. You see, when you listen to the radio and they tell you if you eat a grapefruit every day, you're going to lose weight. You didn't do that experiment that reports this result. The experiment was probably conducted, say, in the States or in the UK. It was probably conducted on, at maximum, a few hundred people. Yet the findings are applicable to all humans. This is the same thing for medications. Okay? If you think of a new treatment for diabetes, it's not tested on Egyptian diabetics. It is tested on, most likely, patients in the States. But the findings are generalized to the whole Earth, and this is the power of experiments. That the findings of experiments, if an experiment is done properly, will generalize to the whole human population. So you do it on 200 people, and then you claim it for the rest of the world. Okay? And without that, experiments would be quite useless, because if I do an experiment on 200 people and my results are only applicable to those 200 people, then there's no use for experiments in the first place. Okay? So we are actually going to study something that's extremely radical. You do an experiment on 20 Egyptians and you generalize to the whole world. Okay? There is nothing similar to this way of doing things in sciences or even in social studies. That's why experiments is in the core of many disciplines, many academic disciplines. Okay? And the same thing for businesses. Okay? Obviously, with businesses, it gets a little bit tricky, and that will become clearer as we talk about how you design an experiment, because a business could actually design an experiment in a flawed way just to prove their claim. Okay? And then that would be an ethical issue, number one, and number two, that would be something that will be discovered, because there are rules to design experiments, and the rules are very clear, and anyone who knows about experiment design, when they read whatever the company is claiming, they will immediately recognize that what they are actually claiming is bogus. The second takeaway is that the first and most important step in an experiment is to determine the type of research question. Are you talking about X greater than Y, X related to Y, X causing Y, and so on? Okay, so this is the first and most important step. Now let's go through the steps of actually designing and running an experiment. So first you design the experiment before running it. Designing means choosing an independent variable, developing the hypothesis, choosing the design paradigm, defining and choosing the control procedures, and then finally choosing a sample size. Once we've designed the whole experiment, we've specified what we're going to do in each of those criteria or each of those categories, subcategories, we're going to do a pilot experiment or a pilot run. And in the pilot run, we just bring a number of people and we try the experiment on them just to make sure that it's going to work. And if it turns out it's going to work, we run the actual experiment. While running the actual experiment, we're going to collect lots of data, and then finally we analyze the data and interpret the results. So let's see one by one what does each of those things mean. The first thing I'm going to tell you is that when we run experiments on users, we call them participants because they participate with us in the experiment. Historically, they used to be called subjects, and you will see in old research papers they are called subjects. I mean research papers dating to 1960, for example, or on old textbooks. Now, but this is again not acceptable anymore. We now call them participants. They're more politically correct term, and they actually the term involves some kind of empowerment to your participants because they feel they are participating in a scientific inquiry and they will help you by performing as expected in the experiment. Okay? Now, something else which is very, very important. In order for us to generalize our results to the whole population on Earth, we have to randomly pick the participants. Randomly means we will pick half males and half females. Unless we're designing a product only for males or only for females, it doesn't make sense to actually pick the other gender. Randomly also means we're going to pick participants from the different classes of the society. So we're going to get people who are, semi-educated versus educated. We will get people who are university graduates versus college graduates versus secondary school graduates. We will get people who are professionals, who are technicians, who are medical doctors. We will get participants from every segment in the society. Okay? If we have different races in the country we are doing the experiment in, we will get participants from every race that exists in the country. If we have several languages in the country, we will get participants from different languages that, or ethnic groups that exist in the country. So, if you think of a university, for example, community, that's not a very good actually pool to draw from because there is some level of homogeneity in the students in a university. All of them are within the same age group. All of them more or less would be exposed to the same education prior to the university, and during the university they will be exposed to a limited number of majors. So obviously it's even worse if you decide to bring all your participants in an experiment from the engineering department, for example, or the faculty department, the faculty of engineering department, because they will all be engineers. Well, you need engineers and pharmacists and business men and or business students and artists and product designers and so on. So basically you are going to randomly select your participants. This is very important because when you randomly select the participants, you guarantee a representation of every member of the society and consequently every member of the human family, if you like, or the human race, if you like. Okay? So you can still screen, by the way, your participants. For example, if you're doing an interface for left-handed people, you can definitely give them a questionnaire at the beginning, and if they're right-handed, you disqualify them. And you mention that in your publication or in your research that, okay, I've done this interface for left-handed people, so and I screened out people who are right-handed. So there is really no issue there. You could screen, according to any objective criteria you like. The important thing is to be objective. So again, if you're developing an interface for females or a product for females, it doesn't make sense to get males, okay? So you can screen out even by gender. But the important point here is that you should not screen to guarantee your results. And this is probably what some companies who are not following the ethical guidelines for doing experiments would do. They would pick the participants whom they know that they will give them good results. Okay? And obviously, you can see this in all kind of practices, not just business. Okay? For example, when you interview people for to ask them about politics, for example, you would pick, this is the ethical version, the unethical version of doing it. You would pick the group of participants whom you know a prior what answers they will give you. And then you go and said, oh, I asked 50 people and they like this. Yeah, well, you picked the 50 because you knew that they will all like this. Okay? So, screening is acceptable, but objective screening that is not made with the intention of manipulating the results. Okay? Now, to explain the different subcategories we need to consider in designing an experiment, I'm going to use the following example. Let's say I would like to test participants' response to light and how fast humans can respond to light. So I'm going to do the following experiment. I'm going to use a light bulb and I'm going to connect it to a circuit, and it will be switched on sometimes fast and sometimes slow, and I tell my participants, each one of my participants who are doing the experiment, when you see the light is getting turned on, click the bell. And I measure the time it takes them to click the bell. And I am recording how fast the light is coming out from the light bulb. So this is my experiment, naive experiment. And by the way, typical psychology experiments, most of the psychology experiments are actually quite simple. You will be surprised how simple they are, because usually psychologists like to investigate basic processes in the human mind or in the human reaction. So whether it's cognitive psychology or perceptual psychology or motor psychology, it will all be very basic experiments, things like what I'm describing here. So anyway, so this experiment is going to evaluate the user response to light. Now let's understand how actually we're going to go about designing this experiment. The first thing we're going to talk about is the independent variable. We need to define in every experiment the independent variable. The independent variable is what we as experimenters are manipulating. Okay? This is what we are changing for the participant. The participant has no control in this change. We are making the change, the experimenters. Okay? We could have several independent variables in an experiment, but within each independent variable or under each independent variable, we should have at least two levels. A level is a specific value for an independent variable. For example, in our experiment here, I have one independent variable, which is the light intensity, and I have in that independent variable two levels, low intensity and high intensity. Okay? I could have also added, for the sake of the experiment, zero intensity, but it does not make sense, because when I manipulate that, when I change it to zero intensity, which means the light bulb is off, the user is not going to ring the bell. And I'm interested to test his reaction, so I have to have some light coming out from the light bulb, and consequently I will just consider low intensity and high intensity. Okay? So again, an independent variable is what you are manipulating in an experiment, what you are changing. The value that you are changing is going to be called level. And at least you should have two levels so that you can compare them against each other. Okay? In the textbook and in some areas, this will also be called condition instead of level. So you must have two conditions at least in an independent variable. Okay? So instead of level, we can call it condition. Now, what you are measuring is called the dependent variable. So what you are manipulating, what you are changing is called the independent variable. What you are measuring is called the dependent variable. And it's called the dependent variable because it is dependent on the participant. What you measure is dependent on the participant. One participant will be fast, another one will be slow. One participant will be sleepy, another one will be awake. So it is the number you measure, because experiments is all about measurements. What you measure is dependent on the participant, and that's why it's called dependent. Okay, so remember it this way. Now, in our example here, in our experiment, we're going to measure the reaction time, which is the time that elapses between the light going on and the user hitting the bell. And this will be the reaction time. Okay? Now, by the way, in HCI, we could measure many things, and in experiment generally, there are many things to be measured. We could measure reaction time, as I just mentioned. We could also measure accuracy. And accuracy is related to the effectiveness of a user interface. You know, the more errors the user make, the less the interface is usable. We could also measure physiological measurements. For example, we could measure how much the interface helps the user to remember a certain item or the location of a certain item. Or we could measure his emotions, directly or indirectly. Or we could measure, as you have seen earlier with the brain, we could measure the concentration of the user by measuring his brain signals. So we could measure many things. Anything we measure will be called a dependent variable. Okay? We could also measure, by the way, the user responding to or responses to a questionnaire. We will talk about that later on. So that's also something that is measurable. Okay? So you could, for example, conduct an experiment on which you try to evaluate the impact of introducing a certain product in a specific segment of the society, and the way you collect the data is you go to this segment of the society and you give them questionnaires and you collect the responses, and the responses will be turned to the responses is a dependent variable. Okay, that's what you're measuring, and you will turn that into numbers and then do the statistical analysis on it, as we will see later on. Now we come to the very, very important and entertaining topic of hypothesis. You must have some kind of hypothesis about what you are changing or what you are manipulating or what you are trying. For example, going to our keyboard example, we had good old Chinese keyboard for 60 pounds, Microsoft keyboard for 500 pounds, and X keyboard for 750 pounds. If I make an experiment and I'm the inventor of X keyboard, my hypothesis is that my keyboard is better. Okay? So every experiment must have a hypothesis. You must have some claim. You must believe in something. Otherwise, why are you doing the experiment? Okay? Now, we will need to differentiate between the hypothesis, what you believe in, the reason why you're doing the experiment, and the nullification and the negation of the hypothesis. Now, the nullification of the hypothesis is that there is no effect. Okay, so if you say keyboard X is better than Microsoft keyboard and any standard Chinese keyboard, that's your hypothesis. The nullification is that keyboard X is not better. No one is better than the other. All keyboards are the same. That's the nullification. Now, the negation is something else. If I say my hypothesis is that keyboard X is better than Microsoft keyboard and is better than standard keyboard, the negation is that keyboard X is worse than Microsoft keyboard and worse than a standard keyboard. That's the negation, the not. If you remember from your early computer science education, we have this not operator. Okay, if you say not something, it's the opposite. Okay, so if I say negation, that means keyboard X is worse, not better, worse. It's the opposite, worse than Microsoft keyboard and the standard keyboard. But nullification is something else. Nullification means they're all the same. There is no better. Okay, I nullify the fact that any one of them is better than the other. Okay, so now it's clear, I hope, what is a hypothesis, what's the null hypothesis, what's a confounding hypothesis. Now here is the problem. You set up an experiment, which means you decide on the independent variable, you decide on the dependent variable, you run the experiment, you publish the results, and someone will tell you, oh, everything you did is fine. I know you did a good job in collecting the data, but I have another explanation for the results you are producing. That other explanation is, we are going to call it confounding hypothesis. Okay? So this is a competing hypothesis that the experimenter tries to neutralize. You try to avoid any confounding hypotheses. Okay? You have to control the experiment in that sense to make sure that there are no other explanations apart from the result you present. Okay? Now, the notion of confounding hypothesis and null hypothesis are very important, and they are actually, and to your surprise perhaps, the weakest point in the experiment design methodology, even though I already mentioned that experiments are extremely popular, extremely powerful, and perhaps they are the only tool really we have to do the scientific inquiry or the scientific thinking correct, or in a proper way. What's the issue here? The problem with the hypothesis, as you will discover later on, is that we cannot prove anything. We cannot prove any hypothesis. Okay? We cannot prove any hypothesis. All what we can do, as you will see later on, we will calculate the probability of the null hypothesis, the chance of the null hypothesis being true. And if the chance of it being true is less than 5%, we will make an unscientific jump and propose our hypothesis. Okay, let me say this again. All what we will do in the statistics, when we come to the statistics part, is to calculate the probability or the mathematical chance of the null hypothesis. How much we can claim that the null hypothesis is true. It's the chance of that being true. And we will set a threshold. We will say, okay, if we find that the chance of this null hypothesis is less than 5% to be true, let's say it turns out to be 3%, so it's less than 5%, we say we will reject it. That's how it's said in the scientific community. We will reject the null hypothesis, and we will put forward our hypothesis. But this action that I just mentioned is a jump from the scientifically proven to the non-scientifically proven. The scientifically proven is the probability of the null hypothesis. The non-scientifically proven is that our hypothesis is actually the reason why we are seeing the results that we are seeing. The problem always will be that someone else will say, yeah, I believe you did a great experiment. And yeah, I've seen that you've done the calculations correct. You didn't do any error in the math. Your null hypothesis probability is less than 5%. So you are right to reject it. But the problem is when you propose your alternative explanation, which is your hypothesis, you were wrong. There is another explanation for what happened. Okay? Now I'll tell you an example of how far this goes. One of the issues that rose in the 1960s when people realized that smoking causes cancer is their the fight that was launched by some user groups and families of patients who died because of lung cancer. And what they did is they went and sued tobacco companies. Now, tobacco companies are very cash-rich companies with deep pockets, lots of money. After all, tobacco is all about burning tree leaves. So tobacco trees are not expensive to grow. So you're basically making money out of burning paper. Okay, so they had lots of money, and consequently they had very good lawyers. And what the lawyers did is that they went and studied the scientific process and doing experiments, and they realized that there is a hole there. No one can prove anything. Okay, we cannot prove anything. We're working on the chance of the null hypothesis, and then we make an unscientific jump and claim that our hypothesis is actually true. Now, all what they needed is not to attack the studies, but to find another explanation. And there was always another explanation. For example, in one case, in one lawsuit, the city where people sued the company had asbestos factories. So the lawyers went and asked for the bodies of some of the diseased patients to be dissected so that they can check for asbestos in their lungs. And once they found the asbestos in the lungs, and obviously asbestos was a cancerogenic material and it remained in the lungs, once they found asbestos in the lungs, they claimed that people got lung cancer because of asbestos, not because of smoking. And every time there was such a lawsuit, it would be nullified by another explanation. There was always another explanation. You always find another explanation. Okay, especially if you deal with experiments that will involve factors that will take years to develop, like smoking. Okay, because people don't get cancer from smoking 10 cigarettes. They have to smoke for a while to get cancer. And not all who smoke will get cancer, so it's a little bit complicated. But the point is, lawyers relied a lot on confounding hypotheses. And because in the States they have this precedence rule that if there is a lawsuit and the judge issues an order or reach a judgment, and then a similar lawsuit is filed, the first lawsuit affects or must be taken into consideration the judgment of the judge. It varies from state to state, but this is a general rule that they have there. And so as people kept losing cases against tobacco companies, as it has been proven to be harder and harder to actually sue them because of confounding hypotheses. So when we do experiments, we have to watch out for confounding hypotheses. That's the message here. So what do we control? Now, in an experiment, we try to control everything that will interfere with the performance of the participants. So for example, in HCI, if you ask participants to type on a keyboard to measure the typing speed, if you make the temperature too cold, the temperature of the room too cold, they will type faster. If you make it too hot, they will type slower. So what you need to do is to fix the temperature to be the standard temperature for humans to perform in an ideal setting, which is 25 degrees. Same thing for the noise. If you're recording from the brain and you're doing an EEG recording and the room is noisy, users will be stressed out from the noise, and that will reflect in the EEG. Okay? Same thing for the lighting. If you switch off the light in the room, people will tend to get relaxed. If you turn the light too much, okay, or perhaps if the user is facing the sun directly by sitting beside the window, the performance will be affected. So you have to control the lighting. It has to be proper lighting. The room has to be well lit, but not to the point where the user is irritated. Why are we doing all this? We are trying to control things in an experiment so that the performance we measure is just the performance of the user in standard setting, instead of being in an exceptional case or an exceptional setting. Okay? We will call each of the things that we are controlling control variable. Okay, so we will control, there's a control variable for noise, control variable for temperature, control variable for lighting, and so on. And this has to be done in all experiments. So even to the point that most researchers will not really report it unless there is really something unique about what they're doing, because it's expected that when you do an experiment, you control things that you don't want them to affect the experiment. So typically in an experiment, we would follow what's called a control procedure just to make sure that we're not affecting the user performance in any way. Okay? We are trying to eliminate any confounding hypotheses. Okay? So what we are trying to do here is that we are trying to eliminate all differences except the ones that we create by manipulating the independent variable. And we will eliminate differences by fixing things at the standard level, whatever that means. So standard room temperature, standard room lighting, okay? Also, part of the things you control is that you don't bring users to an experiment way late at night. Like you don't do an experiment at 9 p.m. because most people at 9 p.m. their body would have switched off. They're preparing themselves to go to sleep, or they're tired from the day that they have experienced. So it's not normal to bring someone at 9 p.m. to do an experiment. Okay? Neither it is normal to bring someone at 6 a.m. to do an experiment. Okay? So what you need to do is you're targeting average human performance, which is going to be during the daytime. And you would even control it to the point that if what they are doing what the participants are performing in an experiment will differ if they do it, say, in the morning versus in the afternoon, then you fix it for all participants in one of the two times. So you get all the participants at 10 a.m. in the morning, for example. Okay? So if, for example, you're doing an experiment to measure the effect of taking a heavy breakfast on user concentration. So you ask them to take a heavy breakfast, you specify the breakfast to them, and then you bring them 2 hours after the breakfast to do the experiment. So you have to fix things in a way to make sure that you're getting the readings you want without interference from other variables in the environment that might affect your recording of the results. So we're going to control lots of things in an experiment. Okay? We're going to control gender by bringing half females and half males. We're going to control ability if there is a need to do that. We're going to also control experience. So depending on our experiment, we will decide what kind of experience. Do we need all kinds of experiences on a specific area, or do we need someone who's just an expert? So if we're covering experience in general, then we will get low experience, average experience, and high experience. Okay, we will also do things related to the administration of the different parts of the experiment. Okay, for example, when we talk to the participant about the experiment, we're not going to look him at the face, we're going to read from a piece of paper. Because if we look him at the face and we're tired, he will get affected by our mood that we are tired, and he himself will be slowed down in the experiment. If we're too excited, then he also will be too excited, and his performance probably will be a little bit faster than what you expect, or what he will do if he was not influenced by your excitation. Okay, so we are going to read the instructions from a piece of paper and not facing the user directly. Okay, we will control settings, noise, light, and everything, as I already mentioned, and we will also control how we present the user with the different components of the experiment. So whatever he's going through in an experiment, we will control it in a way to make sure that there is no part that makes him too tired versus other parts. So let's first, before we go into the details of this, define what's a trial. So a trial is a combination of levels or conditions, one from each independent variable, administered at the same instance to the user, and a measurement of response follows immediately or starts immediately until the user provides a response. So for example, if I have two independent variables, independent variable 1 that has two levels A and B, and independent variable 2 that has three levels C, D, and E. So independent variable 1 here could be, for example, temperature, so I will have low temperature and high temperature. Independent variable 2 could be humidity, for example, so I would have, that's if I'm testing, I'm assuming here, I hope you're getting the idea, I'm assuming that I'm measuring the humidity and temperature on the user effect on the user performance. So I will have low temperature, high temperature, and low humidity, average humidity, and high humidity. Now in a single trial, I will expose the user to one level from temperature and one level from humidity. This is what you see in the table at the bottom right. Trial 1 has level A from independent variable 1 and level C from independent variable 2. Trial 2 has level B from independent variable 1 and level C from independent variable 2. And it goes like this. Okay? So now you know what is an experiment. An experiment consists of trials. In every trial we will have a measurement. Okay? So we're not doing it once, we're doing it many times, as you will see. Okay? But it's very important that in any trial you will have one level from every independent variable, and all of them will be displayed to the user, exposed to the user at the same instance, all of those levels. Okay? So if I'm measuring the effect of temperature and humidity on the user performance, and I say I would like to have a trial where I have high temperature and low humidity, once the user goes into this trial or start this trial, immediately he should experience the high temperature and the low humidity, regardless of how actually I'm going to do that. Maybe I'm going to, set the room on fire or whatever. I don't care. But the point is, he has to be exposed to high temperature and low humidity immediately at the same instance. Now, what we're going to do is we're going to group the trials in a block. So what is a block? It's a set of trials. Okay? This is what is written here. A block is a sequence of trials presented to the user one after the other. So the user will see one trial at a time. So say in the block there are 20 trials. So when the block starts, when we start running the experiment, the first trial is administered to the user. This is how we talk about it. And then we do the measurement. And once we are done, we display the second trial to the user. And then we do the measurement. Once he's done, we display the third trial to the user and we do the measurement. And at the end, after the 20 trials, we will, store on the hard disk or inside the computer that for trial 1, that was his time. That's his measurement. Okay, that's what we measured. If we're measuring time, that means we're after efficiency. If we're measuring the number of errors, that means we are after effectiveness. Okay, so for every trial we could record in a file the amount of time it took him and the number of errors he made, for example. Okay, so this is what a block is. So usually in an experiment we would define and write down what's called a protocol, which is the sequence of steps involved to perform an experiment. The reason why we are writing it down and specifying it, because we would like not to change it or do some arbitrary sequence of events in an experiment. So to fix things, we're just gonna, like as if we're hard coding them, we're just gonna write it down. And this is what we use to explain to the user what he's going to do in an experiment. Okay, he's going to follow a specific protocol, and we tell him about the protocol. Next, we're going to come to the entertaining topic of sample size. What we're doing is pretty radical. What I'm telling you is, we are doing an experiment on, say, 100 people, and then we generalize to the whole world. So you will tell me, okay, we've discussed before the issue of participants being randomly selected, but even if I randomly select them, how come I can generalize from 100 people, from 100 participants to 7.6 billion people? And here is the issue. What we are referring to here is called, first in the experiment world, it's called the sample size, or generally the N. The question is, what is good N? Because you will tend to tell me the following. You tell me, yeah, if I would like to generalize to 7.6 billion people on Earth, shouldn't I be doing the experiment on like 20,000 or 30,000 or perhaps 50,000? Okay? How come I can just do it on 15 people and I can generalize? So I will tell you, okay, you're talking about the sample size now. So let's talk about the sample size. What is a good sample size? Is it 15 or 20 or 10,000 or 50,000? The sample size is related to something called the effect size. Okay? What is the effect size? Effect size is referring to the difference between the conditions you're having in the experiment. In other words, it's the difference between the user reactions to the different conditions you're having in the experiment. That difference is what is called the effect size. Okay? The rule is, if the difference between the performance of the user across the conditions, or within the conditions, or between the conditions is huge, you don't need a huge sample size. If the difference is small, you need a relatively big sample size. So let me give you my entertaining example. I always like to give this example. Let's say you just came from Mars. You just landed on Earth from Mars. And for some reason on Mars there are no fires. So you see fire for the first time in your life. And then you look to these crazy humans and then you say, okay, I would like to test the effect of fire on humans. So you grab a human, because you're too powerful, you just came from Mars, so you are an alien and you're a strong alien, okay? So you grab one of these humans, you light up fire, and he was standing there beside the fire, wondering what's going on, calm but afraid, and just looking at you, and then you put him inside the fire. The difference between his state before being put in the fire and while in the fire is huge. He was standing still, looking at you, and when you put him in the fire, he starts screaming. That's the effect size, the difference between his behavior before and after. Before, standing still, not in the fire, and now in the fire, the second condition. So here I have one independent variable, which is fire, and it has two levels, no fire and fire. The difference between the participant state in the no fire level and in the fire level is huge. I mean, he was standing there, yeah, maybe afraid, but he is not screaming and burning. And when you put him in the fire, he's doing whatever, okay? Now, this difference in the user reaction is called the effect size. So if the effect size is so huge, like how many humans are you going to burn to figure out that actually fire hurts humans? Hopefully just one, if you're a sane alien, okay? Now, again, the story goes like this, the rule is like this. If the effect size is big, you don't need lots of participants. In fact, I can tell you a more kind of realistic example. There were several studies done on Buddhist monks and Carmelite nuns, Catholic nuns, while meditating or immediately after meditating. If you think of an example of a Buddhist monk, actually one of the first or earliest studies that was done on a single monk. They compared his brain signals to the brain signals of an average human being, and there were differences. Now if you think of it, why? Because a typical Buddhist monk would go to the mountains and stay there in the mountains uttering the religious prayer they do for hours and hours every day, and they could stay up there in the mountain for like years alone. So if you compare, if you get someone like this and you're comparing him to a regular non-Buddhist monk, basically an average human being, if there is a difference, you don't need to test, you don't need to evaluate 20 Buddhist monks. One is enough, because the difference is going to be huge if it exists. Okay? If it exists, it's going to be huge, because of what he's doing is quite abnormal compared to the regular or average human being lifestyle. So if there is a change that happened in the brain, you only need one. And in fact, the first study that was done on Buddhist monks only was done on one human being. Okay? Now the other study that was done on Carmelite nuns, it's a Catholic order, I believe the number was like 6 or 7. Okay? And again, that's a very small number, because the study was about changes in the brain from meditation, and only with 6 or 7 the researchers were claiming that there were changes in the brain, okay, and how the brain waves are reacting to the different scenarios after the meditation and so on. So you don't need lots of participants if the effect size is huge. Now if the effect size is small, you have a problem. You gotta increase the number of participants, or your sample size. You're going to increase the n. The classical example I would like also, I also always like to draw on are pharmaceutical companies. Okay, now pharmaceutical companies create medications to treat patients, and the effect of a medication might not appear right away, or the side effects of medications might not appear right away. So they usually conduct experiments that would last for years. Okay, unlike HCI, where we can do an experiment in 2 hours, a pharmaceutical experiment could last for like 5 years, and the participants are in sometimes the tens of thousands of participants. Okay, so they might do an experiment. Big companies like Pfizer and Glasgow and so on, they could do an experiment on 15,000 people that would last for 5 years. Okay, why? Because the effect size is so small. Okay, because if you manage to treat a disease, unless it's some kind of a virus that you will immediately obliterate the virus from the human body. For most diseases, they continue on as a life disease that people will always have, like diabetes and so on. And so most diseases are actually for management. Most medications are for management purposes, like to control the diabetes, or to control the heart problem, or to control the high blood pressure. Okay, the medication is to control. It's not to get rid of the problem. It's just to manage the problem. Okay, if someone has a heart problem, he should go and do an operation to actually fix his heart. But the medications is not going to fix his heart. They're going to just give him an ability to live a relatively healthy lifestyle and a normal lifestyle. So the medication manages the problem. Now the problem is, with these medications, the changes that happen in the patient condition are very slow, and they could contradict with a lot of other things that happen. For example, he could have other diseases, or during an experiment he could die from other diseases or from the disease itself. So when they do an experiment, since the effect of introducing medication is small, given all the variables that might, and all the issues that might happen in the user body while actually being on medication, the effect size is small. Okay, the effect size is small, and consequently they test on huge numbers of people. And since the tests are going to last for a long period, because they would like to investigate the long-term effects of the medication, and since many people of them could have other health problem, and some of them will actually die because of other reasons, or because of the problem they are trying to treat, the experiments will be done on thousands of people and will last for years. Okay, so again, the sample size is related directly or is based on the effect size. Extremely small effect sizes will yield or will force you to go very big in the sample size, but huge effect size will give you the luxury of actually picking a small sample size. Now in HCI, for most of our studies, we are happy with 12 to 15 participants. And the reason why for most of our studies we are working directly or invoking the human muscles, and all humans are very alike in their muscle structure and in their generally how they react to changes in the user interface. So 12 to 15 has always been found to be acceptable for most HCI research, which is good news for you. If you're doing an HCI experiment, then at least you don't have to worry about recruiting hundreds of people to do your experiment. And you don't actually also have to run it for long, because a typical HCI experiment will just last for a few hours to be able to collect the data you would like to collect. So let me read this. It says effect size is simply a way of quantifying the difference between two groups. For example, if one group had an experimental treatment and the other has not the control, then the effect size is a measure of the effectiveness of the treatment. This is another way to state what is the effect size. And here is my entertaining example. Assume you come from another planet. You want to test if fire is more powerful than ice. You decide to conduct an experiment. Independent variable, the media with two levels, fire and ice. Here I change it a bit. Dependent variable, number of screams people are making when you put them in fire versus what you put them in ice. Now, how many humans you need to put in fire to learn it is more effective? Hopefully just one, because the effect size is huge. Okay, that's a big effect size. Difference between impact of level 1 fire and level 2 ice. Big effect means small sample size. This is a summary of what I was just saying. Now, here is another thing. Assume you design a new keyboard layout and form. You don't know if your design is better than the traditional keyboard. You decide to conduct an experiment. Your independent variable is going to be keyboard type old and new. Your dependent variable, the number of words typed per minute. The effect size here is small. If you look at this example, what I'm describing here, I'm using my dependent variable as the number of words typed per minute. Okay? Now, why am I saying the effect size is small? Because we humans all have the same hands, the same motor skills. So regardless of how fast or how great your design is, if the average human typing speed is 15 words per minute, you should not expect that your new amazing keyboard that has this great design will bring the 15 up to 100, for example, because we are limited by our motor structure, how our fingers are tied to our hand and to our palm. So there's no way we can jump from 15 to 100. At the end of the day, if we increase the 15 by 50%, that means it's going to be 22 or something. Okay, so it's a small increase, a small difference. Okay, and that is again another example of what I say as a small effect size. We will increase from 15, to 20, to 25. Okay, that's still a small effect size. Okay, so you will be tempted because of the small effect size to increase the number of participants. But the thing is, the more participants you add, you're not going to get better results, because we are testing basic motor skills, and all humans are the same, more or less. You could think of exceptions, but they're really exceptions. You could think, for example, of Messi in football and his ability to maneuver between humans as a skill that is quite rare. But almost all humans, when they play football, they don't act like Messi. Okay? They are regular people. Their ability to maneuver and grab the ball and run is quite comparable to each other. So you don't need to uncover it. And this is again why in HCI, any number between 8 and 20 is usually acceptable. Okay, and especially if you go above 12 to 20 is for sure is acceptable. Okay, no one is going to argue with you and tell you you didn't have enough participants, because you're testing motor skills. Okay, and motor skills will never be twice or thrice or 4 times faster because of your interface, because you're limited by the human configuration of the muscles. I hope that's clear now. So what's an experiment then? It's a protocol to invalidate the null hypothesis, if you'd like to think of it in a formal way. Okay? The protocol specifies how the participants perform the trials. And you have an apparatus that you write, that you develop, that maybe consists of software and sometimes even hardware, to be able to do the experiment. So in some sense, it's a fake setup, It's not the real thing. You're actually creating an environment to be able to measure the user performance. Okay? So let's go back to the issue of controlling things. We need to control for what's called undesirable effects. So I've stated them here as problems that we need to address in any experiment. The first problem is that the participant performance is best the first time a block is administered. Why it's the case? This is very much applicable in the case of HCI. There is a concept called the novelty effect. When users or participants are presented with a new piece of software or a new hardware gadget, they get too excited because of the popular belief that technology helps people. So if you're showing them a new keyboard, for example, design like Keyboard X that was mentioned at the beginning of the slides, they will get too excited when they see it. But we're not after that performance, because that performance is a little bit biased, and it's faster than what you really should be finding in terms of their performance. So what we do to solve this problem is that we repeat the block 3 times. So we run the block 3 times just to make sure that we are getting the average performance of the user. If he gets too excited at the first block, the second and third block performance will balance out the excitation, or the enhanced measurement that you've recorded in the first run. And so we will calculate the average of the performance in the 3 blocks. Okay, so this is the standard protocol of doing experiments, is that we repeat the block 3 times. So I can tell you now what's an experiment. An experiment consists of 3 blocks, where every block consists of a number of trials. And the 3 blocks are really a repetition of each other. The second problem we also need to take care of, and all of these are under the notion of controlling the experiment to avoid confounding hypotheses, is that participant performance is affected by the order of the trials in the block. So by accident, you could have ordered the trials in the block so that the first one is either making the users upset or making them too excited. And you don't want either. You don't want to make them too excited, you don't want to make them upset or tired even. But you will not know up front, and especially that you will get participants from different backgrounds randomly selected, so you will not really be able to judge which one is better to put first. So instead of thinking of it that way, what we're going to do is we say to rotate the trials within the blocks. So you see here the 3 blocks we talked about and why we need it. We already described that. Why do we need 3 blocks? But if you look inside, what's inside the block, I don't have the same sequence of trials. So block 1 has trial 1 followed by trial 2 followed by trial 3. Block 2 has trial 2 followed by trial 1 followed by trial 3. And block 3 has trial 3 followed by trial 1 followed by trial 2. Okay? So I am rotating the trials within the block. And this is done in all the 3 blocks. So if there is any one trial that is problematic, that is causing the user's performance to go either way, too excited, too fast, too slow, too bored, too tired, it will be nullified by the other, or averaged out, not nullified, averaged out by the placement of other trials in its place in the other blocks. The third issue we have to address is that the participant performance is affected by the order of the blocks themselves. So maybe by rearranging the trials or rotating the trials within the block and doing that for the 3 blocks, you've created an amazingly difficult or challenging or depressing or exciting block for the user. So what we're going to do is we're going to rotate the blocks on the participants. So as you see here, if you get 4 participants, not every one of them will see what everyone else is seeing in terms of order. Participant 1 will see block 1 first, will have to do block 1 first, followed by block 2, followed by block 3. Participant 2 will do block 2 first, followed by block 3, followed by block 1. And I've listed above this table that you see at the bottom what is inside each block. So as you see, I am rotating the trials within the block. So block 1 has T1 followed by T2 followed by T3, block 2 has T2 followed by T1 followed by T3, and block 3 has T3 followed by T1 followed by T2. And now I'm also rotating those blocks within the participants. So I'm trying to nullify the effect of anything weird in my design or my order of things. Okay? And since I cannot figure that out because I will get a randomly selected number of people, the best thing is just to do these rotations to average out the performance. Okay? So the takeaway is that in an experiment we rotate trials on the blocks and we rotate blocks on participants to avoid unintended influence from a specific order of running trials and blocks. The next thing we need to decide on how actually we administer the blocks or the trials to the participants. Specifically, it's really the trials here that's of concern. We have 2 popular designs. The first one is called within subjects. In the within subject design, all participants will do all the trials. That's why it says here each participant is tested under all conditions in the experiment. And this is what I try to highlight by the table at the bottom. You see I have 4 participants. This is just because the screen is small, so I couldn't put more participants, but basically I have 4 participants and every one of them is doing everything. Participant 1 is doing block 1 followed by 2 followed by 3. Participant 2 is doing block 2 followed by block 3 followed by block 1. So he's also doing block 1, he's also doing block 2, he's also doing block 3. Everyone is doing everything. Okay? This is one way to do it. And this is usually what you would think of. You know, I'm going to get a group of people and they will do my experiment. That's how would you think about it. But there is another way, and here's the other way. In the other way, you get a number of participants and then you split them into 2 groups. And each group will do half the trials you have. Okay? So, let's look at this example. I have independent variable 1 that has 2 levels, A and B, and independent variable 2 has 3 levels, C, D, and E. Okay? Now, I got 6 participants. So I'm going to split them into 2 groups as the table in the bottom right shows. I'm going to split them into 2 groups. Participants 1, 2, and 3 will do half the experiment. Participant 4, 5, and 6 will do the other half. So if you'd like to map this to our keyboard example, if I have X keyboard versus Microsoft keyboard, 1, 2, and 3 will do the X keyboard, the trials using the X keyboard, and 4, 5, and 6 will do the trials using the Microsoft keyboard. This is what I try to highlight here with this block numbering. So participant 1 is doing block 1A. Okay? So is doing A here means a variation of block 1 that is intended for the first 3 1A here is intended for the first 3 participants, while 2A is intended for the next 3 participants. Okay? Now, why am I doing it this way? Why am I splitting up things? I would split this up because I'm concerned about the impact of exposing the participants to the whole experiment. Sometimes this just does not make sense. I'll give you the classical example first, and the classical example is from the pharmaceutical company. Let's say a pharmaceutical company is trying to evaluate the effectiveness of 2 drugs to treat diabetes. So they bring a group of people, say of 50 people, 50 participants, who have diabetes. And we got these 2 medications. They would like to know which one is better in managing diabetes. They cannot give the 2 medications to everyone. to each one of the 50 participants. Because if they do that, actually it's even dangerous on their life, because part of the medication will control the insulin level, and if two medications are trying to control the insulin level in the blood, the insulin will probably drop to the point that the patient might die. So you cannot give two medications fixing the same problem to the same patient at the same time. So, and plus there is something else. If you give every participant the two medications and they don't suffer from doing that, when they get better, how would you know whether they got better because of medication 1 or medication 2? You wouldn't know, because you've put the two medications in the patient body. So you don't know, is it because of medication 1 or medication 2, or an interaction between medication 1 and medication 2. So you do not know. So pharmaceutical companies will always do the following. Will split their participants and will give one medication to one group and another medication to the second group. And we have a name for this. It's called between subjects design, when we start splitting. Now there is actually an advantage, apart from this notion that sometimes it's just wrong to actually do within subjects, which is the one we've seen in the previous slide, just because of, similar to the example I was just mentioning. There is another issue with between subjects. It will actually enable you to run an experiment faster. Because if an experiment is taking 4 hours and you would like to speed up the execution of an experiment because you're running it on too many participants, if you split it and do it between subjects, everyone will do 2 hours only. So you can run an experiment in parallel and finish faster. Okay? But that's a minor added advantage. The main issue is that you're concerned about what we describe as confounding effects, that what is administered to the participants in the first group of trials will affect how they behave or react, or what you record in the second phase of the trials, or when they see the second level of the same independent variable, which is exactly the example of the medications I was referring to. Okay, so we have two ways to run the experiment. It's called experiment design, either within subjects or between subjects. And this is the takeaway. There are two ways to design an experiment: between subjects and within subjects. Now let's see an experiment that was done many years back. And it is actually the reason why we have now these great integrated development environments like Eclipse and NetBeans and IntelliJ if you use it, and so on. Okay, so this was done, I believe, 40 years ago. And the hypothesis of the researchers was that it is actually better to beautify source code, instead of just displaying it as a sequence of lines. So what they argued is that the source code appearance could enhance the comprehension of code. Okay? So this is what they did. They used two presentations. First of all, they used the C language, okay? They used two presentations. They decided to compare two presentations. The traditional presentation, which is what you see here, just a listing of code, and a more visually appearing, visually organized presentation, which is this one. So you see here, there is indentation. There are thick lines and thin lines. There are areas in light gray background, and there are areas that are just plain. And they are playing well with the placement of variables. So you have the parameters displayed after the method name, and then there is a line, horizontal line, which has the number 13 written beside it. And then there are some local variables declared, and they even, as you see, are now numbering the lines. Now we have this now nowadays in all IDEs. This is what we're seeing here is even primitive, but by what exists now in Eclipse or IntelliJ or NetBeans and so on. Okay. Or even JCreator, okay? So the point is, when they did this, no one was doing it. And they wanted to claim, they were trying to prove, that was a hypothesis, that this presentation is better than the standard way of just looking at the code. But they had to do an experiment to prove that, because without an experiment you cannot prove anything. Okay? I'm kind of negating myself a little bit here, because I told you that we don't really prove anything with experiments, but I'm just using it the way people are using it. I'm saying we can prove things. Really we can prove nothing. We just work on the probability of the null hypothesis, and that's basically it. But basically they wanted to say that we did an experiment, and the experiment is showing that this is better. So this is what they did. They have one independent variable, the presentation. They have two styles or two levels, the new typesetting format and the traditional presentation format. And the dependent variable here requires some thinking, because they were after the comprehension of the code. So the only way you can judge the comprehension of the code is if you give developers a piece of code and then you ask the developers about the code, what do you think this is doing? And that's what they exactly did. Okay, they would show the developers a piece of code, a relatively complex one, and then they would ask them questions as if it's an exam. They would tell it, okay, what's the purpose of this code? How many variables existed? How many for loops? What was the for loops doing, and so on. Okay, and the number of questions answered correctly is the dependent variable they are measuring. That's what they are measuring. How many questions were answered correctly? Now the null hypothesis obviously is that reading comprehension will not change between the old and the new. It's going to be the same. And what they did is they used within subjects design. So all participants did the whole experiment. But here they had to take care of something. They had two presentations. So it does not make sense to show the same piece of code using the two presentations and then ask about the same piece of code twice. Because when you see it in the first time, you will understand it regardless of whether it's the new presentation or the old presentation, and then you're going to answer the questions about it. When you see it in the next time, you're not going to even read it because you've seen it before, so you're just going to go ahead and answer the same answers that you've given in the first time the second time. What that means is they could not show the same piece of code twice to the users, once with old presentation, another time with new presentation. They had to change the code, and that's what you see in the next slide. They've run this on 44 students, and the apparatus was two similar but not identical short C programs. Okay, why similar? Because they are doing within subject design. So every participant will see the two conditions, the new presentation and the old presentation. So they couldn't have used the same program, the same C program, I mean. Okay. And the protocol was 40 minutes to skim each program and attempt to answer 18 questions. Now they got those results. Okay, for every participant there is the number of correct answers using the old presentation and the number of correct answers using the new presentation. And as you see here, we have some numbers. The question is, what should we do with these numbers? What we should do is we should do statistical analysis. Now let me tell you a little bit about statistics here. There are two types of statistics you can collect: what's called descriptive statistics and inferential statistics. Descriptive statistics is what you learned even since your preparatory school days. Okay, mean, median, standard deviation, mode, and so on. You display them in pie charts, you display them in bar charts. At the end of the day, they're just descriptive statistics. They describe the data. You cannot use descriptive statistics to come up with conclusions about the experiment, because they just describe the data. They don't make any inferences. Inferences means conclusions that are applicable in the future on all human beings. Okay, you cannot do that on or using descriptive statistics. You have to go to inferential statistics. Inferential statistics means using statistical models to talk about the performance in front of us. Okay. Now, here is the problem. We have hundreds of statistical tests, okay? And the differences between any of them is actually quite small, but it's important, okay? What that means is we have a lot to choose from, and if we check any two, we will find that they are quite similar, but not identical, which means we need to be careful in choosing the statistical test, because if we choose the wrong statistical test, all our findings will be negated. It will be completely flawed. Okay? So, how do we go about choosing the right statistical test? The first thing we need to know about statistical tests or inferential statistics is that the normal distribution plays a pivotal role that cannot be overestimated in inferential statistics. Okay? Remember, the normal distribution is this bell curve, sometimes even called Gaussian distribution, of values, where you have the majority of the points in the middle, in the big area. Okay? That's exactly in the 68% of the curve. And the sides of the curve go very close to the zero, and they get smaller and smaller. So 13.59 and then 2.14 and then 0.13% of the total data that you've collected on both sides. And 0 is in the middle, and 0 is actually the mean, the average of your data points. Now, the majority of statistical tests assumes that the data that you have collected from the participants is normally distributed, which means whatever you measure from the participant, you plot it on a curve or a graph paper, and then you draw a line on the top of the data points. You will get this bell curve that looks like the one in front of us. You will get something that looks like this. It's going to be a normal distribution. Okay? So the first step when you collect data from the participants is to test for normality. There are tests, you will see them in the tutorial, for testing that the data follows the normal distribution. Without that condition, if you fail that test, if your data fails that test, you have a problem. You cannot continue on and do the statistical analysis because the data has to be normally distributed. Okay? So the first step is to test for normality. If you pass the normality test, this means your data is normally distributed. So we're happy. We move on to the next step, which is to remove outliers. Now, outliers are values that are far, far away from the mean towards the extremities of the curve. And usually they are measured as the mean plus or minus 4 standard deviation. So the mean exists in the middle where the 0 is. You measure the standard deviation and you multiply that by 4, it's going to take you all the way till where it says 4 plus sigma. Okay, the standard deviation. Now, any point after this plus 4 sigma or minus 4 sigma on the far left of the curve, any point there, we're just going to exclude them from our data. Now, we will see why that's the issue. Before we do that, we have to understand, what if the data is not normally distributed? What if you collected some data and then you test for normality and the test fails? The test comes out telling you this is not normally distributed data. Okay? Your first choice should be get more participants. Remember, what data points exist under the normal distribution are points coming from participants. If you don't have enough participants because you overestimated the effect size, so you got a small sample size, the reason why you will not be getting a normal distribution is because you have some missing points. So if you keep getting more random people, more random participants, they will generate points that will fall on the graph in the proper location, so then the next time you test for normality, it's going to be normal distribution. So your first attempt should be get more participants. Okay? Now, there are sometimes situations where the data that we are collecting is by definition very close to each other on the graph. And we can expand this data, stretch it out, and this is an ethical issue we're doing. We're not manipulating the data in a malicious way. We can stretch it out by taking the log of the data. So we apply the log function, and that stretches the data a little bit, and so we will have our normal distribution. Okay? And you would say in the research paper that you're writing afterwards in the experiment, I took the log of the data, to fix the normality problem. Okay, so you can do that. Now we come back to the issue of outliers. What's the problem with outliers? Why are we removing mean plus or minus for standard deviation? Okay, statisticians would argue that points that are far, far away in the extremities of the bell curve are coming from a process that is different from the process that is generating the other numbers that exist on the curve. Okay? So, and this is what is said at the bottom point you see there. It says normal data objects follow a generating mechanism. Example, some statistical process. Abnormal objects deviate from this generating mechanism because they're not being, they're not coming from the same statistical process. In other words, from the same mechanism that generated the other points. Okay? So when we exclude them from the data, we're not maliciously manipulating the data. We're cleaning the data from points that have polluted, if you'd like, our data because they come from other sources. Okay? So for example, I'll give you an example. You do a brain study on participants. And while you tell the participants, if you are taking any medication that affects the brain performance, please don't come to my experiment because it will affect your brain recording. You get this participant who is taking antidepressants. And he's passing through tough times, so he took, a little bit of an overdose of antidepressants. So when you do the experiment on him, his brainwave gets affected. He's actually slower than any other participant you have. So his data point will appear at the far extremity of the curve. And when you run the outlier test, actually, you see that you should eliminate his data point. Okay? Why? Because the performance you're seeing from him being too slow is due to a process that you're not really supposed to be recording from, which is the introduction of antidepressants into the human brain. Okay? So, statisticians would usually agree that removing outliers is a good idea. But not all researchers would remove them. Sometimes they are just kept. It's up to the researcher to decide. Okay? One thing is you need to test how many points are, outliers. And if they are just a handful, very few points, whether you keep them or remove them will not affect your final result. But if there is a good percentage of them, you have to wonder about your experiment and your recording, and you have to decide about whether you should remove them or not. Okay? Now, this is another way to talk about the same problem. You would see in statistics book, this being argued that data is usually multivariate, i.e. multidimensional. Whatever you measure is coming from different interleaving processes in the environment, in the user brain, in the user body, So what you need to make sure of, you have a process that generates numbers and you're measuring from this process and you're not measuring from anything else. It's another way to say what I was just saying, that the outliers will be coming from a different process than the one you're actually measuring from. Now I have here a very entertaining story. I'd like to mention it every time I talk about outliers because it shows how important outliers could turn to be. Outliers actually became famous in the history of statistics because of a case that we went back all the way till goes back all the way to 1949. You have this gentleman, Mr. Hadam, who went to the war and came back to find his wife having a baby. Now, the problem is she had the baby, according to her story, Mrs. Hadam, after 349 days of pregnancy. The average human pregnancy is about 280 days, which is 40 weeks. So 349 days is a lot of time to be pregnant. That's about 60 days more, actually 70 days more in terms of pregnancy time. So obviously there was an issue between them, and he said that that's not my baby. And she said, oh no, that's your baby. So they went to court. And the question turns out to be a statistical question. Is it possible that a lady would be pregnant for 350 days compared to the normal 280 days? And to her bad luck, actually, there were tons and tons of studies made by doctors as a research activity, about the human gestation period. In fact, in one study that I show here, the picture from, the study was made on 13,634 females who got pregnant and how long they stayed pregnant. So with such a big N, the statistics becomes much stronger. And the conclusion was that 350 days is unlikely to be a human gestation period. In other words, this point is an outlier. In other words, she was lying. She was not pregnant for 350 days. You see on the curve here where she appears on the 50th week. Okay? Studying 13,634 females, all of them finished before the 50th week. So her claim was just impossible. And her data was considered as an outlier, or her claim was considered, an outlier. And consequently, the case was ruled that, this was not Mr. Hadlam's son. So this shows how outliers could be used. I mean, it's a very important concept in statistics and in the experimental world, as you see here from the chart. And you can entertain yourself with the same content here, except this is a slightly better graph from another textbook. The takeaway is that the first two steps in analysis of the data collected during an experiment is to test for normality and to remove outliers. This is the course textbook with a reference to the experiment design part, and I have placed it on 2 locations, on Dropbox and on Google Drive. So try to download it and read the experiment design stuff if there is something you feel that you didn't capture in today's lecture. And next time we will start talking about the statistics.